We started the chapter by looking at areas of parallelograms and triangles, and in 10.2, really all we're doing is adding in the same areas but for trapezoids, rhombuses, and kites. So we can find the area of a trapezoid when I know the height and the lengths of its bases, kind of like in your parallelogram, although in a trapezoid you should have two different base lengths. The height of a trapezoid is the perpendicular distance between the bases, just like we saw the height for parallelograms earlier. And if I'm making a formula for the area of a trapezoid, it's going to be half the product of the height and the sum of the bases. So I can write that as area is half height times the sum of the bases, which is base 1 plus base 2 added together. Another way you can think of that formula is it's the height times the average of your two bases. So if I add my bases together and divide by 2, multiply that times the height, that'll get me the area. So just like with parallelograms, most of our work is going to involve looking for those two base lengths and also the height, plugging those in and simplifying for our area. So in our first question, if we're using that trapezoid area formula to find the approximate area of Nevada, first of all, this should work because it's roughly trapezoid shaped. If I use the left and right hand sides as my two parallel bases, again, maybe not quite parallel, but close enough for our purposes, I can use that as base length 1 and base length 2. So I know that's 205 miles and 511 miles. If I'm looking for a height, again, height doesn't always have to go up and down. As long as I'm going perpendicular from one base to the other, that'll be a height. So I can use the height here would be 309. So if I just take those three measurements and plug them into my formula, 1/2 times the height times the sum of my bases, I should be able to simplify that and end up with 110,622 square miles, which should be pretty close to our area of Nevada if we look that up. So next question, using that same idea, if I want to find the area of a trapezoid with the height given as 7 centimeters and bases given as 12 and 15 centimeters, again, we're just taking those measurements and plugging those in, substituting in the formula. So for my area, again, that's going to be half of the height times the sum of the bases. So height would be 7, bases are 12 and 15, so that would be a sum of 27. And if I just substitute all of those and multiply, 1/2 times 7 times 27 should come out to 94.5. And again, got to be careful of our units there. We got to use square centimeters as units for an area. So same kind of questions on the back. We're looking for the area of our first trapezoid. Although here we're going to have to remember some rules from our last section. In our last chapter, if I'm given lengths of 5 and 7, I can use those for my two bases, although we're not given a height to start this question. We're going to have to find that. So we do start by knowing there's a 60-degree angle in that bottom left-hand corner for angle P. And if I draw a line for my height, again, a height would just be a perpendicular segment that goes from one base to another. We should be able to find our height using our rules from our special right triangles. And if I first find that the opposite side of our upper base would be 5 for the lower part, that means that if the entire bottom base is 7, that would be a 5 plus an extra 2. So if I made that separation, my little triangle off to the left here would have a base length of 2. And if we go back to our 30, 60, 90 right triangle rules, we should be able to solve this without using our calculator. If I take the side across from the 30, that was your short side. So if I start with 2, to get from the shorter leg to the longer leg in our 30, 60, 90, we take that measurement and multiply times rad 3. So our height here should end up being 2 rad 3. Now that I know all three of those, I know the two bases from the start of the question, and we used our special right triangle to find the height. Again, I'm just going to substitute those in my formula, and I should be able to simplify and solve. So our height, again, was 2 rad 3. Our two bases were 5 and 7, so if I add those together, I get 12. 1/2 times 2 rad 3 times 12 should get me 12 rad 3. Simplest way you can think of that is just the half times 2 would cancel, and then we're just left with 12 rad 3 at the end. So same type of question, although if I, instead of using a 60, if I flatten that figure and used a 45-degree angle instead, that would make your height a bit shorter. And I didn't draw out the entire triangle, I didn't draw out the entire trapezoid, but the triangle that we're looking at off to the left would be pretty similar. Instead of a 30, 60, 90, now it's going to be a 45, 45, 90 in this question, if angle P is now 45. So if it's 45, 45, 90, we still have the 2 that's left over from one base on the bottom minus the base on the top. So if one leg is 2, for a 45, 45 triangles, the other leg should be the same. So last time we had to take that and multiply times rad 3, but this time if it's 45, 45, they're both the same, so now my height is just 2. And now that I know those three measurements, I should be ready to substitute. So if my height is 2, and I've known my two bases from before, if I substitute those in my trapezoid area formula, I should end up with 12, and that would be square meters. So also besides trapezoids, we can find the area of a rhombus or a kite, this time if I know the lengths of its diagonals. So not base and height this time. Now I'm looking down the middle of that figure and trying to find diagonals. So again, taking that same rule and putting that into a formula, area of a rhombus is half the product of the lengths of its diagonals. So that would be like diagonal 1 times diagonal 2. Doesn't matter which one is 1 or 2, as long as I'm multiplying those two diagonals together. So trying that in our first problem, where I'm trying to find the area of this kite, KLMN, it looks like I'm given a length of 3 and 3 meters. So if I add those together, that diagonal length of LN would be 6. If I take the 2 and the 5 meter measurements and add those together, my other diagonal would be a length of 7. So again, I'm not going to take them separate. I'm just going to add them together and find the entire length. So if I'm plugging those into my rhombus area formula, that would be 1/2 times the diagonal we found first times the diagonal I found second. So that's 1/2 times 6 times 7. That should give us 21 square meters. If I try another question and this time use the diagonals of 12 inches and 9 inches, these I can just substitute directly into my formula. Again, for a rhombus or a kite, it shouldn't matter what formula we're using. If I take 1/2 of diagonal times diagonal, that's 1/2 12 times 9, and that should simplify to be 54. And remember, since it's an area, I got to use square inches for my units. So a couple questions to finish here, which is finding those in a little bit more complex figures. So if a carpool lane is marked by these series of diamonds that we'll see on the road, and diamonds are just going to be rhombuses because all my sides should be the same length on the outside. Those are painted on the pavement. We want to find the area of that rhombus in the carpool lane. It's a little bit hard to see the units that we're using there. So I wrote those a little bit bigger. We're given 2.5 as basically half of the diagonal going horizontally. And we're also given 6.5 as the length of the rhombus itself. So if we're just given those two pieces to start, again, to finish this, we should end up knowing the lengths of both diagonals. And I could find one diagonal length by taking 2.5 and adding another 2.5. So one diagonal length should be 5. The other one we're going to have to find with some work. And I set that up here. If I know that the diagonal length is what we're going to be trying to find, I can use this as a right triangle, and I should be able to use Pythagorean Theorem. So whatever length that's missing, I call that x. X squared plus 2.5 squared should be equal to 6.5 squared, since that's the hypotenuse. So if I set up that equation to find my missing length, I should be able to isolate and solve for x. So take away 2.5 squared, and once I take a square root, square root of 36 should just make that missing length 6. So now I know that half of that diagonal length is 6. That means the entire diagonal going from top to bottom should be a length of 12. So if I just go back to my area formula, area of that rhombus is going to be 1/2 one diagonal, which is the one we just found, that's 12 going up and down, times the other diagonal, that's one going left and right, that was 5 all put together. So 1/2 diagonal times diagonal gives us an area of 30 square feet. Same type of question to finish. If I know a rhombus has sides which are 10 centimeters long, again, sides is going to be along the outside of your figures because your rhombus is that entire shape. We know the longer diagonal is 16 centimeters, so 8 and 8, if I break that up through the middle, I want to use that to find the area. So this time our missing length is just going horizontally. So same steps. I know that if I want to find x, I can use Pythagorean Theorem, because that would just be half of the length of the diagonal. That's just going to make a side of a right triangle. So if I set up x squared plus 8 squared to be 10 squared, I should be able to solve for x from that and get x is a length of 6. So just like in the last question, if 6 was half of that diagonal, I also know that 6 will be the other half. So if I am looking to substitute in my area formula, area again is 1/2 diagonal times diagonal, so that would be 1/2 16 if I combine the vertical diagonal, and 12 if I combine my horizontal diagonal. So 1/2 diagonal times diagonal should end up with 96 square centimeters. So be sure to try those workbook questions, and we'll see how we did on that when we come back to class.